Quantum computing is one of those topics that somehow gets presented in two completely opposite ways. Either it is described like the future of all technologies, or it is explained in a way that makes you feel like you first need a PhD in physics. Instead, I want to show the broad spectrum of quantum computing and navigate to the topics that are interesting from the perspective of software engineers, developers, and people who are comfortable with code but do not want to be buried alive under physics. First of all, a quantum computer is not just a faster computer. It's not like your laptop evolves and suddenly your code runs 1 million times faster. That would be nice, but that's not how it works. Quantum computers are special purpose machines that can only be useful for certain kinds of problems. So, if your dream is to run Chrome with hundreds of tabs more efficiently, well, classical computers are still handling such abuse. At a very high level, quantum computing is a different model of computation built using the laws of quantum mechanics. Now, before you panic and run away because I said quantum mechanics, relax. For this channel, I'm not going to begin with the dramatic physics monologue involving Schrödinger, dead cats, and the emotional damage. You do not need to start there. Think of it like most programmers use SSDs every day without first studying semiconductor physics in painful detail. As software engineers, we only care about the abstraction layer that helps us build useful things. Same idea here. Well, you do need some basic concepts, yes, but to start learning quantum algorithms, what matters more is understanding what kind of machine this is, what kind of problems it can help with, and how to reformulate or express hard problems in a form that this machine understands. And quantum hardware is also not just one thing. It is more like the hardware evolution we already know from classical computing. For example, we had floppy disks, CDs, flash drives, then hard disks, and we have SSDs. The goal is same to store data, but very different underlying technologies and trade-offs. Just like the hardware to store data is still evolving, the new quantum hardware is also like that. There isn't just one magical quantum computer. Because the basic building block of a classical computer is a bit, the physical component which works as a bit is a transistor that obeys the laws of classical physics, and the best possible material currently in use is silicon. Similarly, for a quantum computer, the building block is a qubit. Mathematically, a qubit is a vector in a two-dimensional Hilbert space, and the basis states are typically represented using Dirac notation as ket0 and ket1. But for a simpler understanding, the basis state of a qubit is a binary column matrix. Anyway, we will not get into this direction, at least for now. But the point here is only a physical component that exhibit quantum mechanical properties can act as a qubit, and what's the best material for it is yet to be found out. There are multiple hardware implementations, each using different particles as qubits. First, we got superconducting qubits. This is the most mature industrial technology used by companies like IBM Quantum and Google Quantum AI. Then we have trapped ions. This architecture is known for very high precision and is used by IonQ and Quantinuum. Next is neutral atoms. Notable providers include QEra and Pascal. Then we have photonic systems, mainly are pursued by companies such as PsiQuantum and Xanadu. Apart from these universal gate-based computational models, we have a significantly different computing paradigm focusing mainly on optimization called quantum annealers. The most well-known company here is D-Wave, which also use superconducting qubits. All of these platforms are aiming at useful quantum computation, but they are not interchangeable implementations of the same machine. They differ in control mechanisms, error characteristics, scalability, and ultimately in the kinds of workloads they can handle. So the phrase a quantum computer hides a lot of architecture underneath it. Also, quantum computing is not just a single topic. It is a whole stack of areas and different communities care about different parts of that stack. Fundamentally, there is the problem of building the machine itself. This part is mostly dominated by physicists, hardware engineers, material scientists, and experimental researchers. This includes things like the science of how qubits work, the control systems used to manipulate and measure them, and the challenge of making them stable enough to hold information reliably. Then there are topics where physics and computer science meet more directly. This includes quantum error correction, quantum communication and cryptography, quantum sensing, and post quantum cryptography. These are areas partly about physics, information theory, and designing systems that are either enabled by quantum mechanics or protected against future quantum attacks. And then there is the part that I think will be especially interesting for software engineers and computer scientists, which is quantum algorithms and applications. This is the layer where the main question becomes, what kind of computational problems can be represented in a way that quantum hardware can offer a computational advantage? That is where this channel will spend most of its time. For people coming from software, the interesting part of quantum computing is not about memorizing physics buzzwords. It is understanding computation, basically understanding what kinds of problems are easy, what kinds of problems are hard, where do classical methods scale nicely, and where do they start to struggle, and how do we reformulate hard problems into something a different computational model can tackle. That is why quantum computing becomes interesting. Because at that point, it stops feeling like an abstract science and you will start thinking about the algorithmic design and implementation. Less of assuming it as a physics magic and start thinking about the computational advantage it can bring. And this is also where I want to be very honest. Quantum computing today is heavily hyped. Some people talk about it like it's going to save the planet, destroy encryption, and solve every problem known to humanity by next week. Well, that's not true. Current quantum hardware is noisy and limited in size. We are very much in the phase of this is promising, but please calm down. Most computational tasks today are still very much classically viable, and for a good reason. What is interesting is understanding the narrower set of hard problems where quantum methods may become useful, especially on near-term devices. So this channel will focus on quantum computing from a practical engineering perspective. We will cover just enough of the surrounding landscape and focus more on what is real, what is implementable, and what is useful. Basically, what a software engineer can actually sit down and code, with the main focus on quantum algorithms, optimization, QUBO and Ising formulations, variational approaches, quantum annealing, and most importantly, real-world applications in areas like machine learning, computer vision, finance, and scientific computing. And yes, implementation matters. Python code, tutorials, reproducible examples, and actual problem formulations. Because if a topic cannot eventually be connected back to code, models, or computational workflow, then it again becomes too abstract. So if you are a software engineer, student, or just someone technically curious who wants to understand quantum computing without starting from the complexity of quantum mechanics, this channel is for you. Again, to repeat, the goal is to build useful solutions using quantum computers. The approach we take is by treating the quantum computer as a black box, but understand how to formulate a real-world problem into a form that is processed by the quantum computer to obtain the solution. Such an abstraction helps in avoiding the mechanics of the hardware. Just like how we write functions in code, we are mostly making sure what the function takes as input and what it returns as output. Or making an API call, we create abstraction by just agreeing upon a request and a response schema. In the next video, we will begin with one of the most important ideas in practical quantum computing about how a surprising number of hard problems can be converted into a form called QUBO, and different quantum algorithms to solve them. Once you see that, a lot of the field starts looking much less mysterious.